Hello, I'm Luke Weston from the School of Earth Sciences in the University of Bristol. So I'm going to move away from landslides for a bit and start talking about remote sensing of volcanic ash clouds, and more specifically the problem of having an unknown size distribution when carrying out retrievals. To start things off, I'll talk about what we currently know and what we currently don't know about volcanic ash airborne size distributions. Then I'll go on to talk about how and why we need these, or how we use these size distributions in infrared remote sensing and why we need to make certain assumptions. And finally, some of the implications and uncertainties attached to not correctly knowing the size distribution during these retrievals. So a bit of motivation. I'm sure you're all aware of the 2010 Eyjafjallajökull eruption. I'm sure it affected many of you, or otherwise you probably knew people who were affected by this. There was a loss of over 1.7 billion to the airline industry alone, and it caused the biggest closure of airspace since World War II. So airline safety is one of the main focuses when it comes to volcanic ash clouds. In terms of airspace closure, it's generally controlled by dispersion models, but also increasingly remote sensing techniques are being used to sort of validate these dispersion models and correct them, and even things like data simulation to work as source parameters for driving these dispersion models. So what do we know about volcanic ash size distributions? There's been about 15 papers published on airborne size distributions over time. These started in the 1960s, went up to about the early 90s, and then there was a brief hiatus then until the 2010 eruption. So these have been done using manned aircraft. So these distributions here, just a sample of a few of the size distributions which have been measured. At the top, we have some measured in terms of the number distribution, then their surface area distribution, and then finally your volume or mass distribution down at the bottom. If we look at these central distributions, these are quite polymodal distributions. There's been very little distinction between volcanic ash and other atmospheric aerosols, and this is true for quite a lot of the early measurements of airborne size distributions, and it's quite hard to fit any sort of mathematical size distribution to these. Over on your right, we have some ones done in the 80s and early 90s. They also have this polymodal type distribution, but they're slightly smoother, and then sometimes we can make slight approximations in terms of mathematical shape to these. And over on the left, we have some of the measurements from the 2010 Aya eruption. And all these measurements have been truncated at 12.5 microns as well, just for comparison. These over on the left, so this is the lognormal fit to the coarse mode, which was assumed to be the volcanic ash mode in their airborne measurements. But even with these, depending on what sort of assumptions we make about the particles themselves, such as the size or the composition, we can have a varied fit to our size distribution. But so, for example, the eruption of Eyjafjallajökull was shown to be lognormal. This is true for about another 5 measured airborne ash size distributions over time. In terms of the geometric standard deviation, or the spread of the values in this lognormal fit, we've managed to match to size distributions. They've ranged between 1.2 and 2.5 as their geometric standard deviation. And then this really controls the spread. And if you look at the graph there, it really shows quite a different sort of distribution depending on this number. So now if we move on to remote sensing, here we have an image using the Severi sensor on board the Meteosat second generation satellite. This is our brightness temperature, which is a function of radiance, at 10.8 microns. And you can the darker areas are colder parts of the atmosphere, or colder parts in our observation, and the lighter parts are warmer areas of observation. So these colder areas are generally our clouds and also some volcanic ash. So if we play a game of spot the volcanic ash, it's really quite hard to distinguish between this meteorological cloud and volcanic ash. What we can do then is look at this at 12 microns. I'm sure many of you didn't even realize that I changed the image there, but it looks fairly similar. We can try and sort of get an idea of how hard it is to distinguish between these two things. But luckily, if we minus one of these images from the other, we have our brightness temperature difference between 10.8 and 12 microns, the brightness temperature at these wavelengths. We see this dark patch start to emerge in the middle of the image here, and this is our volcanic ash cloud from our 2010 Eyjafjallajökull eruption. We can also change some of our thresholds to show what sort of brightness temperatures we display. So this quite dark patch then is our ash cloud. And there might be some false flags, but this can be we can get rid of these by adjusting our threshold slightly. So what I did, or what's generally done, and what was noticed was that ash will have, for a given brightness temperature difference and brightness temperature at 10.8 microns or around here, particles will have their own unique size and mass loading, that's massive ash as sort of a column in the atmosphere, for a combination of these brightness temperature difference and brightness temperature at 10.8 microns. So we define our size of our distribution in terms of an effective radius, and this is essentially a volume to surface area type ratio of a distribution of particles. It's quite a convenient way to characterize a distribution of particles. So what we do is then we'll forward model particles of different sizes and mass loaders in the atmosphere and create a lookup table of values which we can then compare to our observations to work out how much mass is in the atmosphere. And that's a nice graphical example here from prior to 2012, where you can just read it off and get your mass loading in the atmosphere. Certain assumptions do need to be made here, such as our cloud top height or our temperature at the cloud top. The surface temperature needs to be assumed. The size of the ash cloud to be assumed a solid slab cloud. But also one thing we do need to assume through this is the geometric standard deviation, or the spread of our distribution throughout. And it's been said that errors of around 40 to 50% are probable using this sort of method. So what I did is I produced 3 different lookup tables with 3 different values of geometric standard deviations, purely based on our observations which we have out there. So our observations of geometric standard deviation range somewhere between 1.2 and 2.5. So I went slightly up from that. I used 1.52 and 2.5 as the basis of my lookup tables. As you can see, in terms of our size of our particles, we can actually achieve quite different sizes depending on which geometric standard deviation we use. If we then look at this in terms of mass loading, this becomes even more pronounced. We can actually gain order of magnitude difference in our mass loading between a 1.5 geometric standard deviation or a 2.5 geometric standard deviation. But actually, I mean, what does this mean? What does this mean in the real world? Well, we can convert them to the European Aviation Safety Agency contamination levels in the atmosphere. So the green areas are deemed areas where the ash concentration is low enough to fly in. We have our medium contamination level, which is similar to very stormy clouds. It's perhaps possible to fly for a defined period of time. And we have our high contamination level, which is a complete no-fly zone. And you can see by purely a different assumption, this geometric standard deviation, we can completely reclassify air contamination zones based on these European levels. But if you put yourself in the situation of someone producing one of these lookup tables, prior to 2010, all values of this geometric standard deviation were somewhere between 1.2 and 2.1. So if we're making a lookup table based on observations, we'd probably be closer to the situation over on the left. During the eruption, FAM, the UK facility for airborne atmospheric measurements, or aircraft atmospheric measurements, found geometric standard deviations of somewhere between 1.8 and 1.9, which would probably push us towards this central situation where the DLR, who are the German equivalent, found a geometric standard deviation of 2.5, which puts us over in the situation over on the right. So it's really quite unclear what the correct sort of value to use would be in this sort of situation. This is quite easy to explain using the physics. If we look at our mass extinction coefficient, so this is our scattering and absorption per unit mass, it really differs for a given effective radius. So most of our ash will be in this sort of 0 to 5, 0 to 10 range of effective radius size. And our properties are really quite different for a given effective radius, depending on which geometric standard deviation we use. I mean, we're very much in the Mie regime of scattering here. So, in conclusion, we really don't know much about volcanic ash. We don't really know much about the extreme values. We assume often a log-normal distribution, but if this is universally valid, it's something we don't really know. Our mass loading uncertainty can really yield order of magnitude differences if we base it on our in situ measurements. And then finally, we really need to have a better understanding of these volcanic ash size distributions if we're going to improve our remote sensing techniques. Thank you very much. Yeah.